My main goal in this video is to come up with a definition for logarithm, but I want to start by considering the exponential function y equals 2 raised to the x power. So let's start with a graph. We know that this will be an exponential growth model because the base is bigger than 1. And we can plug in these very simple values for x just to get a pretty good sketch. So just plotting my points. And I know this exponential function is going to have a horizontal asymptote here on the left-hand side at y equals 0. And then I get that exponential growth shape as it grows. And there's my nice happy graph of y equals 2 raised to the x power. And we could go on and write down that that would have domain, all real numbers. And the range would be everything larger than 0, not including 0, because that's where that horizontal asymptote is. And now, looking at this function, I realize that this exponential function is 1-to-1. It passes the horizontal line test. Every x is assigned a unique y. Which means this function y equals 2 to the x must have an inverse function. So instead of thinking of this as y equals 2 to the x, let's just call it f of x is 2 to the x. And I want to think about the inverse function. I want to graph f inverse. And I feel like I can do this without even knowing a formula for f inverse because I know what happens to the domain and range, right? This domain and range, this was the domain and range for f of x is 2 to the x. When I write down the domain and range of the inverse function, well, the domain becomes the range. The range becomes the domain because the most important thing we know about an inverse function, and that should be 2 raised to the x power, the most important thing we know about an inverse function is that we swap x and y. So in looking at my table here, if I wanted to graph the inverse function, all I would have to do is swap the roles of x and y. Right, literally just swapping my two columns, my inverse function should go through these points. So let's plot those points and see what happens. At x is 1/2, I would get out a -1. At 1, 0, I have a point on the inverse function, and at 2, 1. And I remember that inverse functions are symmetric with respect to the line y equals x, so I should graph a mirror image. One really cool thing is this graph had a horizontal asymptote at y equals 0. Well, when I find the inverse function, I swap x and y, so this equation y equals 0 would become the equation x equals 0, which instead of being a horizontal asymptote would be a vertical asymptote. And so there's the graph of my inverse function. All right, so because my function was 1-to-1, I knew there was an inverse function. Because of things I know about inverse functions, I was able to write down the domain and range. The domain, all the positive things, and the range from -infinity all the way to infinity. All the y values would get hit. And apparently this thing has a vertical asymptote at x equals 0. And so now I think a good question is, what is this function we just graphed? Well, the original function was y equals 2 raised to the x power. The first step to finding an inverse is to swap x and y, which would make this x equals 2 raised to the y power. And then our next goal would be to solve for y. And if we don't know anything about what we're getting ready to talk about, there's no method of doing it. But I can tell you what y is, right? I need to get y by itself, which is basically saying, hey, tell me what y is, right? This says y is 2 raised to the x power. Well, if I think about this, y is the exponent that 2 is raised to in order to get x. That's what the inverse function is going to be. Whatever we write down, y equals the exponent that 2 is raised to in order to get the number x. So the inverse relationship, x equals 2 to the y, and once we have y by itself, it'll be some kind of statement that says this: y is the exponent that 2 is raised to in order to get x. Well, this is supposed to be a function, so if we plug in an x, we're supposed to get out a y. So I want to think about that sentence as being my equation, and I'm going to plug in a value of x, and we're going to see if we can figure out the exponent that we would raise 2 to get that number. So I could say something like 8. All right, so 8 goes here. So I'm looking for a number that is the exponent that 2 is raised to in order to get 8. Well, 8 is 2 to the third power. So y would be 3. I could ask for 4. What exponent do you raise 2 to get back to 4? Well, you get 2. If we plug in 2, the exponent clearly should be 1, and this is a function. And we can think of it as this complete sentence. It's not a real nice way of writing that down, so we have notation for it. And the notation is this: y is equal to the logarithm base 2 of x. This is notation for this statement. Now, I want to rigorously define logarithm, but the most important thing is that every time I write down a logarithm, I can convert it to an exponential statement. And the logarithm itself is the exponent that the base, this number, is raised to in order to get x. Here's the formal definition of a logarithmic function base b. For x is bigger than 0, and we see that x needs to be larger than 0 because of the domain we found here just by starting with an exponential function and finding this as its inverse. So for x is larger than 0 and b is bigger than 0 and not equal 1, that's the same rule for the bases we developed for our exponential functions. Y equals the log base b of x is equivalent to b raised to the y power is equal to x. We've developed notation here to be able to write down the inverse function for an exponential function. Every time I see a logarithm, I can rewrite it as an exponential statement. And every time I see an exponential statement, I can write it down as a logarithm. This is the most important statement anyone can ever tell you about a logarithm. Its relationship to an exponential and the exponential's relationship to the logarithm. This function is called the logarithmic function with base b.